Hello everyone, my name is Badri Adhikari and my poster is on REALDIST, a method for real valued protein distance prediction.
This poster introduces REALDIST, a method for real valued protein distance prediction. The method only predicts real valued distance maps. We use a really large set of around 43,000 protein chains by combining the PISCES set and the CATH dataset and train a variant of residual neural network to make distance predictions. Overall, in table 1, we find that our method performs similar or even slightly better than the TR Rosetta method that is out there on the CASP13 dataset and on the Cameo dataset. One of the novel things that we do in this work is we transform the distance labels using inverse functions such as 100 by D. We actually optimize this to have a much better transformation function such that small distance values become large values. And then once we make a prediction and calculate the loss, it turns out that smaller distance end up having much larger losses so that the model is overall optimized to predict smaller distances more accurately over others. We also built 3D models using the distance maps we predicted, and for proteins that are shorter than 250 residues on the Cas13 free modeling set, we observed that the TME score and other metrics of the top one model that we built is similar to the A7D model method in Cas13. We also evaluated real value distances using some new metrics to evaluate real value distances and compared REALDIST with some of the methods out there like DIPDIST, TR Rosetta, and GAN. Some of the methods have similar precision, but GAN has a much lower precision. In the paper, we discussed this, but then we also evaluated using these distance metrics, carbon beta LDDT, mean absolute error, and Pearson correlation coefficient. Interestingly, we found that REALDIST does not have as good MAE and PCC as the TR Rosetta method. But when we took these distances and built 3D models using Confold, we found out that the models built by the REALDIST distance maps are slightly better than TR Rosetta and much better than other methods. So we investigated why this was the case, and we found out, as we see in this figure 2, that the TR Rosetta method actually is conservative in making predictions. That is, so this is on the CASP13 set. TR Rosetta likes to predict fewer distances than the actual number of distances in the protein. So it's conservative. It wants to make fewer but correct predictions. And interestingly, this actually holds the coverage of the distance map, and that's why this is revealed in the 3D modeling. The models turn out to be slightly worse than how actually they appear to be. And this is also captured by the carbon beta LDDT metric, where we can see that TR Rosetta has a significantly lower carbon beta LDDT. Overall, our method is a typical ResNet. There are a few tweaks that we do to make it slightly different. We use convolution size of 3 by 3 and 1 by 5 alternatively, but otherwise we extract the standard features that we use. We also come up with have some tweaks on the features, but basically it's the similar features that we've been using and use a deep ResNet to predict real valued distance maps. Thank you.